This is my first conference in 2.5 years. Last one was Vancouver, NeurIPS 2019. 2.5 years. And I used to do a few of these talks. I have 2.5 years of material. I have so much to say. I was putting these slides together, and it turns out I don't have much to say at all. So, so I just created a story with a lot of photos. But I think it's an honor to be able to start off the 2-day conference and kind of set the stage of what we're doing. You won't learn anything from me, but I think if there's one way to look at it is that people like Dave and I've played a small part in building a community where we've seen AI go from fringe science into mainstream and having massive impact. So I'll take you through a journey from the academic roots to applying AI in places it really matters, like saving lives, where I'm putting my energy in right now. So let's just go down memory lane a little bit. Neural networks and AI, it's had its ups and downs, it's had its winters, there's been so much promise, and the reality hasn't really caught up to the promise until now recently. So even when at the very advent of computers, when scientists, physicists got into it and they're like, hey, these are cool things, we can program these things, what should we program? Let's program the human brain. And this is their first attempts in 1960, creating the perceptron. Imagine doing MLOps on that. One of those wires is gone haywire. Which one is it? That's the definition of MLOps from 50 years ago. But there's a lot of enthusiasm early on. It turned out to be much more difficult to do. Largely what was difficult about it was just the ability to adjust those weights. Nobody figured out the math until this guy came along. So Jeff Hinton in 1986 came up with a paper around how you can backpropagate errors through a network and fit a loss function. And it's not a trivial exercise at all. It's not one-to-one mapping of input to output. It goes through a series of steps, and being able to adjust each of those things, there was the math on it was non-trivial. This whole story of AI is a story of people with great grit and tenacity being at it for years and years, and then being able to find the signal in the data haystack and creating a prediction out of it. Jeff, I think, embodies that grit. He not only is he smart, his lineage goes back to George Poole, who's the original mathematician that underpins computers, but he's also got incredible grit and staying power. He, in 1973, went in to pursue an academic career in neural networks in a biologically compatible way of doing AI. And he went into the field during one of these cold winters, but he persisted, and 13 years later, he figured out how to train these algorithms. Computers and data weren't up to snuff, so it really took him another 25 years to actually show that they could do anything. And during this time, he essentially worked in obscurity in this building on the second floor of the Pratt building. And University of Toronto, with organizations like CFAR, provided a lot of funding for these very ambitious long-term research projects. But really, he was going against the grain. He couldn't get published. He was relegated into the fringes of computer science in his field. And he just kept at it. And just incredible, his whole journey over 50 years, being able to keep at a field that now is going to transform the world. I myself, I came to University of Toronto to do my grad school at the same time. I had had an interest in neural networks since I was a kid. In fact, back in 1986, I was in high school, and I could have read about these papers, and I wrote a little high school term paper about AI, artificial neural networks. And I kid you not, I thought the concept was that you put like human neural tissue on top of a chip. And that's what I wrote to my physics paper. My teacher believed it. He thought it was great. But I was a little bit off. And I came in after I did my undergrad in Waterloo. I came to U of T and I wanted to study neural networks. But this was in 1996. It was one of those cold winters. Nobody thought it would amount to anything. And I was dissuaded from studying neural networks. My thesis ended up being on cryptocurrency, which is kind of funny in itself. But I did take a lot of courses with Jeff Hinton and ended up then as a career going down to Silicon Valley, where my career took me down the path of first doing machine learning and now more recently deep learning. But where Jeff was kind of still doing the science, going against the machine, there's another school that looks similar to that for people who, does anyone know which school this is? This is the Gates Computer Science building at Stanford campus. And here, statisticians were advancing another field of AI, in machine learning, so fitting data to a set of rules. And there was a paper in 1999 that came out that defined gradient boosting machines, so allowing the computer to program its own rules based on data that it was being fed and to fit a loss function. And just to show how quickly like Silicon Valley can take leading edge research and put it into production, paper was launched in '99 and uses of that was already starting to become apparent in the industry 3 years later. The first application of that was here. Yahoo was the leading email, like web internet mail provider. And one of the major issues that mail providers had was spam. Anybody who's old will remember all those emails that tried to sell you Viagra or some adult service or prescription medication or insurance. Early days of internet webmail was just inundated by spam. And companies like Yahoo would employ armies of people that would write these rules. If body contains the word Viagra and for sale, they're classified as spam. Those things were very brittle, and these human editors couldn't keep up with all the spammers who kept just changing everything. So the very first application of gradient boosting machines was in Yahoo Mail, where it was an offline process. Mail comes in, and before it gets in the inbox, it has a classifier, spam classifier. And the nice thing is that we had already had years and years of labels. So we had human editors and people who had reported spam. So volumes of data to be able to train this algorithm. So that was the first really big use of machine learning, and way better than humans, and it could train continuously. Now, it was interesting and it was kind of fun, but we were solving a spam problem. It wasn't really it was just solving a problem. It wasn't necessarily creating a lot of economic value. And it was also an offline process. I was working in web search at that time, and we had this Canadian chemist. He was a PhD in chemistry, organic chemistry from Montreal. He was playing around with gradient boosting machines in web search ranking. And in the lab, it showed really great promise. But web search is a very different beast than offline spam classification for mail. In web search, you're literally dealing with thousands of queries a second. Consumers expect super low latency, so real time. And when you're ranking web pages, you're ranking millions of pages. So it's like a massive, just the scale of it is huge. And so just for those mathematically inclined coders out there, let me just define what the problem is. So gradient boosting machine results in a series of trees that you have to traverse the tree. So there's a bunch of if-then statements. Each of these trees could be 10 to 20 long. So that's a lot of code paths you have to follow. And the scientists' proof of concept had 20,000 trees. So imagine traversing 20,000 trees to a average depth of 15 across 1 million pages that you find on the web for the web query 1,000 times a second, right? Like, you just can't. That was an intractable problem. So that was actually my second. I had a company in Waterloo when I was an undergrad. That was my first company in data compression. So as a kid, I was a really good coder. And then I wanted to go solve that problem. How do you put machine learning into production? And so that was my kind of second endeavor, and how you productize things, machine learning inference at great scale. And that was really the kind of, if there's an AlphaGo moment in Silicon Valley, that was really it, where web search now is $1 trillion business. And we were able to, at Yahoo, we were able to do something with machine learning in a black box that was better than our competitors in Mountain View at Google could do by essentially fitting a linear model into web search ranking. So before machine learning and web search, it was basically you'd have a bunch of these different inputs. PageRank is one, your TDIF is another one. And then you kind of try to tune all of these little dials. And Google will literally have like an army of PhD sitting around a conference room table debating how you should tune these things. But it was important for them to know and understand how that algorithm worked. It's web search after all. Yahoo, that had by this point in time been trounced by Google in web search relevance, was able to experiment a little bit more. So we essentially chucked the human tune algorithm, dropped in this big black box, and made significant gains in machine learning. And that was really like a huge moment in Silicon Valley and big tech, where you could see enormous amount of value being created from machine learning. Now, this was still traditional machine learning, and unbeknownst to us in Silicon Valley was that Jeff had kept at it. And so while I was building the system that used Intel SIMD instructions to traverse these trees, Jeff and his grad students, Alex and Ilya and others here in Toronto, were using NVIDIA GPUs to train these deep learning networks. Jeff will say that he knew that he had a computational deficiency. He knew that he was always struggling in training these somewhat large machine learning, these neural networks with the computing power he had. But what wasn't apparent to him is that the gap of computing power needed wasn't apparent to him. He thought he needed an extra 10 or 100 times more computing power. Turns out he needed an extra 1,000,000 times the computing power. And the only way to get there was through GPUs. And he did that with his grad students. And this is actually roughly when I moved back to Canada, and I got a chance to reconnect with him and see the stuff that he had been working on in his lab now actually working. And it was funny, my last lecture with him back in 96 or 97, his last lecture, he said, he produced this like theory. He always has another theory of how the world's going to change. He put up this theory, I think it was VAEs at the time, and he was like, this is how it's going to work. I know exactly what I'm doing. It's going to take me about 5 years to figure it out. So that was in 96. It took him 15 years to figure it out, and he had to wait for computing power to catch up to his theory. But like, holy cow, this the amazing like grit of Jeff and his students to keep at it. Now we're in Toronto, birthplace of deep learning. The tech economy here is terrible. There's nothing exciting happening. And in fact, what the typical story here was that a promising tech company is born, then gets picked up by a US big tech company, and they relocate down to the States. That was for acquisitions. It was also for startups. So if a Silicon Valley VC put money into a Canadian tech startup, their requirement was to move down south of the border. That's kind of shown in a slide like this back in 2017. I think I pulled this slide out when I was making a case for why we should have a vector institute. This showed, now 5 years ago, the world map of unicorn companies, startups valued at over $1 billion. And it is so heavily concentrated in the US, in China, some in Israel, but like really US and China is a place where it was happening. We had one company, it's called Kik, back then. It's really crazy, right? One company, which has now gone under. So not much happening in tech. Birthplace of AI, technology that's going to change the world, not a lot happening here. And so, Jeff, myself, my partner Jordan Jacobs, we set out to try to change that ecosystem. Conferences like this is about changing that perception and that reality. And there's a bunch of different venues that changes that. Number one is this guy, Ajay Agrawal, had a new thesis of what it takes to build technology first, like science-focused startups. And he created an incubator called Creative Destruction Lab. That itself seems, it's a huge Canadian success story. But really the theory here is that, if you're building an app and you want some viral growth, Y Combinator is a great place for it. Spend 6 weeks, do a demo presentation, and away you go. But if you're trying to do something really hard, and deep learning is hard, as is biotech and others, if you want to do something different, really hard, you need a different model to it. And so he created this new thesis around incubating science-based, principally science-first startups that had a 10-year kind of a gestation period where a lot of advisors were brought in a 2-month rolling window to help startups. So that's been a fantastic community building effort here. I was one of the original fellows, one of these G7 fellows, and I was the only computer scientist in the room. And I brought in Jeff and the University of Toronto deep learning professors into that fold. So that's one area that's been very instrumental to grounding and anchoring our ecosystem. The other one is just around funding. So we don't want Andreessen and Excel to continue to pick off the most promising technology companies in Toronto. We also want to make hard science-based bets on companies. And there wasn't any local funding that would do that. My partner Jordan and I, we started a venture fund called Radical Ventures that has just had its 3rd close of its fund, but invests in technology, like people with companies that still have technical risk. Companies founded by engineers that have great tech differentiation and ambition and are able to attract people around them. Really focused around AI-based companies, but any deep tech qualifies. So that was another gap that we saw in the local ecosystem, that there wasn't a funding path for it. So that's what Radical Ventures serves. But most importantly, the system still needs the academic roots of the deep learning community. And while there was now all this hype around AI, there wasn't, Jeff had already gone off to Google, and all of his, like so many of the profs were on their way out, and it felt hollow. Felt like, yes, we were, you could say we were the birthplace of deep learning, but with all these profs streaming south of the border, how long was that going to last? We made this pitch to the province and to Merrick Gertler, the president of the University of Toronto, to say that the province, the university needs to double down on these deep learning profs that are going to change the world. There's going to be a tremendous amount of economic value created. We can't claim to be a knowledge-based society and economy unless we credibly own that trough at the top of the triangle that creates most value, which is deep learning. So this is me pitching the Ministry of Economic Development very unwisely in a hoodie. So for those, if anybody ever goes to the province and asks for $50 million to set up an institute, please wear a suit and a tie. This is bad. This is bad form. But that was literally like in the day kind of. They could slot us in, so I kind of jumped in there. But amazingly, the province bought into it. The University of Toronto, Merrick Gertler, the president, supported it. And this is a picture from like a few days before the launch event of the founding team. So you have Jordan, Ed Clark, who's been instrumental, and Jeff, of course, and his students. This is the size of the Vector Institute at the very start. So it was 6 profs and about 31 grad students. That was it, tiny. And in fact, half of these individuals would have left and gone south of the border had we not put the Vector Institute together, because they all told us that there was not enough critical mass. And big tech companies were coming in and buying off talent for millions of dollars. So now the Vector Institute is massive in scale. This is the future home of it. So this building here is the Reisman Schwartz building. They gave a $100 million donation to build this building. That's a corner of college and university. And Vector Institute will occupy the top 4 floors, incredible space. There's 2,000 researchers affiliated with it. 1,400 of them are like master's students that are being trained by them, and then 600 are faculty and their students and postdocs. So just a phenomenal concentration. So academics wanted scale, here's scale. Meanwhile, I was building a company called Layer 6, and for us, it was important to have access to this talent, for there to be a feeder system of graduates coming through there. And here's just a picture of our environment. And we were very successful in serving. We built this general purpose AI algorithm. We found a niche in financial services. Banks have a ton of data. They're terrible at turning that data into value. So we were serving banks, selling to at least about 5 out of 6 banks by 2017 here in Canada. And banks took notice. So here's a few banking executives, look like fine banking executives, and they wanted some AI chops in there, and they made a play and brought us on board. And this is what it would look like. And I still code, so I write these anomaly detection algorithms with deep learning, and I just let the program run, and it found all these anomalies. Max didn't tuck his shirt in. Jordan, that doesn't look like a banker's jacket. And then, that's just me trying to smile. So all joking aside, the bank was a great place for us. The cultures were so different that they let us run completely autonomously. And now we basically built the brain of the bank. So all data flows through Layer 6's AI technology, and the bank makes real-time decisions based on those. Big part, of course, is like, how do you build the infrastructure to actually make this work? And ML Ops is all about the infrastructure. Day one, when we walked in there, we knew within 2 weeks it wasn't going to work. And the thesis was, hey, we buy Layer 6, you guys continue to advance the AI capability and the engine, but we handle all the IT and the ops for you. And it turned out very quickly like that ML Ops is crazy important. You can't do any of it with poor infrastructure. So it took me 2 weeks to realize that this is going to not work at all. And we actually went to our executives and said, you might as well write this acquisition down to 0 unless you change how we operate. And they were awesome. They said, okay, tell us how to do it. And so we had a couple of our scientists, engineers, have their retina scanned. They went to the data centers, and we plugged in our Ubuntu boxes with sudo access and pipes into our office. So like TD was awesome in breaking down, like just making it so available to us to kind of really change how the systems worked. Now, they were themselves in a massive like enterprise data project, and those are like multi-year, $100 million projects. And they build them at the enterprise level, and then they ask the lines of business to pay for it. So the lines of business are like grumbling, like, oh, I got a business to run. Why do I have to put money towards this enterprise effort? What's the value in me? So the executives now will tell me that part of buying Layer 6 was really to show what the carrot is at the end of the road. And that was actually being a great catalyst to then get the whole enterprise on board with this enterprise investment in a data lake. And we were also capable of doing some of this ML work early before it was all stood up. But you know, you don't want to do the stuff in a data center, in your own data center. You really want to do it on the cloud. And you know, I've had this interesting story around first jumping into AWS, and then Satya Nadella inviting our CEO to his lakefront house in Bellevue, and it's just like an amazing, like just watching, having a frontline seat, watching how big tech, big cloud vendors compete with each other. And they're so very different in philosophy. So where AWS, I think technically is by far the most advanced, they are largely hands-off. Like they just expect their clients to be technically savvy and do their own thing with systems integrators often. But if you're not an enterprise that is super confident in your own technology, if you want your hand to be held throughout the process, you go with Azure, because Microsoft is the old IBM of the 1990s. Buying Microsoft or buying Azure, you'll not lose your job as a result of it. And Microsoft will see you through. So it is interesting how even at TD, our business was with AWS at first, then Azure is where it ultimately landed. But cloud is exactly the place where you end up. So at TD, we got the infrastructure going, and we learned a lot, and we have been very successful in deploying AI across the enterprise, largely because when you deploy in a regulated industry like banking, the models need to be very robust, cannot have bias, they need to be able to be audited, et cetera. So going from big tech into a bank, I at first didn't really appreciate what was required. I kind of approached AI a little bit like a Kaggle competition, just optimized for accuracy. But to deploy things responsibly is actually a science in itself. And it's important in banking when you're deciding on a loan to a person. But it's also important in other areas like healthcare, where I am currently. And you know, just quickly end with my most recent pivot into healthcare. I have, so St. Michael's Hospital here in Toronto is recognized as the global leading institute for medicine and AI. And they've had the benefit of having a 6-year run at it. They got a $10 million donation from a Hong Kong billionaire called Li Kai-sheng, who had this phrase. He said, "I want data to help people." And St. Mike's, that effort has been run at St. Mike's by Dr. Mohammed Mambani here. And he basically wrote the book on medicine and AI. It's amazing. Guy in Toronto, nobody's heard of him. And they have deployed clinical AI that's saving lives. And during the pandemic, the hospital leadership came to me, like they tried to give away the AI to other hospitals because it was being so meaningful there. So they came to me and they said that the only way to distribute it this far and wide was to have a private company do it, provide the 24/7 support, do the ML ops, run it in a cloud as a SaaS service. And I signed up, of course I signed up. And I also went to TD Bank and I said, hey, listen, I'm gonna go do this and I want you to license the Layer 6 engine because I think it could be helpful here. And it is. Actually, just last night, we launched our first model that does real-time risk prediction across patients in the general internal medicine ward. And it's literally saving lives. You know, here's just our infrastructure. It runs in the cloud. And one of the things, I'll just leave you with this particular slide. What's super important, what makes this all work is that we've put a huge practice into getting ML ops right, deploying responsibly, deploying with like bank-grade cybersecurity in the cloud. None of this stuff would be possible had I not gone through that TD Bank experience and really learned those capabilities over time. So the Layer 6 platform actually runs, that runs in a bank, also is what runs now at hospitals. And there's mutual sharing of those practices between these entities. So yeah, so that's it. That's my journey from a coder and a scientist to banking to healthcare, where I feel machine learning, I think, has the greatest potential societal impact in understanding human ailments and being able to tailor treatment and medication for better health outcomes for people. So thank you for bearing with me. It's been a pleasure. Thanks, Dave.